I'm just going to talk at you. I'm not even going to talk with you. I'm just not even going to look at you guys. There you go. Just a reminder that when we start this out, that will work. And yesterday we just chose a standard. I mean, there's only one loop here, so it's not like there's a lot of options. So there's your loop. The voltage drops have to sum to be 0. There are 3 voltage drops. And they have to sum to be 0. The circuit's not particularly interesting, but what it does is interesting. And because of that, we start here. Now, let's go with the math. The voltage across the resistor will be based on current, which at time 0 isn't necessarily going to stay constant after that. So I'm going to use a lowercase I here to represent the idea that the current might be changing. And that shouldn't surprise you. The capacitor has to become charged. And although there's no current across the capacitor, there's certainly going to be the movement of charges from one plate on the capacitor to the other, which means the rest of the circuit is going to have a current in it, but there won't necessarily be a current across this little tiny gap right here. You guys follow that? A pretty simple, straightforward argument. So at the same time that we say the potential across the resistor is based on current, we know the charge, lowercase q, on the capacitor is going to be based on the voltage across the capacitor, which at time 0, the voltage across the capacitor is 0. Now, keep this in mind. If at time 0, the voltage across the capacitor is 0, then at time 0, the voltage across the resistor equals the EMF. So it's as if the capacitor doesn't exist at time 0. Does that make sense? All right, so let's make those 2 substitutions. I need to solve that for V, so I'll get Q over C equals V. Now, at the onset, this doesn't look very interesting, except that this is a first-order differential equation. It is because I is dq dt, by definition. So making that substitution, that's our first-order differential equation. Let's stop here for just a minute. Doing this process, should it come up on the exam? This part doesn't actually come up that often on the exam. I'd say you have a 1 in 3 shot of having to demonstrate the charging of a capacitive circuit by using calculus. Generally, they tend to favor of the three FRQs, 2 of them are probably going to involve calculus, but it's very likely that it'll be the electric potential one and then the Faraday's law one that'll probably rely the most on calculus. If they use an RC circuit for calculus, they are probably going to have you establish or set up a differential equation. What we have done generally is all the work necessary to set up a differential equation. They may not have you solve it. That one they do far less often on the exam. We're going to solve it because we have the skill set to do so. But the exam probably won't. That doesn't relieve you of the responsibility of being able to do it. Now, you guys who are in your calculus class, I know you guys use prime notation quite frequently to indicate the first derivative. That only works out if you guys know with respect to which variable you're always taking your first derivative. And for you guys in calc, it's often to x. But I want to point out that in college, they will often use a dot notation. And the dot notation is specific to derivatives with respect to time. So these 2 equations represent the same thing. One is just less cumbersome than the other. But college will assume you know this. They won't teach that to you. So dot notation represents a derivative with respect to time. It is different than prime notation when prime just indicates the first derivative of the function with respect to whatever variable the function has. Prime notation is more generic and less ubiquitous across coursework. But dot notation is very, very specific to time. Okay? I'm going to continue to say this is what you should do. I just try to make sure that you guys have at least a few things going into college that'll help you out. Now, we have to solve this. If solving this circuit means coming up with a relationship between the charge and T, this will tell us how long it takes the capacitor to charge. It'll also give us something that will help us figure out what the current is. But more importantly, from here, we should be able to figure out how the energy flows in our circuit. Hitting pause. All right, I'm going to go to another page that's not so cumbersome and do you realize this product would be the full charge on the capacitor? It's the capacitance of the capacitor times the EMF of the circuit. So on what we have here. So we have R dq dt plus Q over C. Now, we need to split our differential. All I've done is make everything positive, but we have to split our differential. Now, you've done this process before. This one's a little bit more complicated. I'm going to move Q over C to the other side of the equation. So I'll get E minus Q over C equals R dq dt. Now, you have choices on what to do here and how you like to do this. I like to get my differential function completely by itself. So I will divide both sides by R and get E over R minus Q over RC equals dq dt. So all we've done is solve for dq dt. This is the first step in separating a differential. Now, I don't think I need to write those steps down. You've already written those down someplace about how to separate a differential, correct? So I'm just following that set of steps. So you know what I'm going to do next is multiply both sides by dt. And this is going to give me E over R minus Q over RC dt equals dq. So I have successfully separated the differential, but for us to be truly separated, we need to make sure that anything that has T in it is on the side with dt, and anything that has Q in it is on the side with dq. Yes, sir?
Does it matter where you put dt when you're bringing it over? If you put it on the right, like what happens if you go to the left? Would it be any different?
Well, yeah, they're probably out there throwing knives in my Jeep tires. All right, so what we have to do next is probably the harder part, I think, for a lot of you. And to answer Tyler's question, we're eventually going to take the integral of both sides. And so just for tradition's sake, we tend to sandwich the function between the integrand and the integral symbol. But I don't want to take the integral yet because I have Q on the side with dt. Now, you might be reticent to do what I'm about to do, but it's always better if you're going to have to take something like this and move it to the other side of the equation to get common denominators first, so you can just invert the function. So I'm going to multiply both sides by, top and bottom of that one by C to get a common denominator. And this will definitely help the future of this problem. Because now, when I move it to the other side, I will get dt all alone on this side, and I'll get RC in the numerator, EC minus Q in the denominator, dq. All right? Any questions about those choices? All right. Let's take the integral now. So integral both sides here. Let's set our limits. I like to set the limits on the front end of the integral as opposed to doing it as an indefinite integral. I think we can all agree that we're talking about doing this from time 0. And Q represents at this moment the charge on the capacitor. Right? It's the only thing that has Q in it. So at time 0, the charge on the capacitor is 0. We assumed it started uncharged. And at some point in the future, we will be at, you know me, I like to use the same variable for t, just another t. If that's going to confuse you, I could put a capital T there. But am I okay with just a little t? Capital T tends to stand for period, and I don't want to use that here. At the same time, I will use capital Q here because that's going to represent what the charge is on the capacitor sometime in the future. A lowercase q would be fine there too. I need a placeholder for the q as a function of t. So I don't have to do any work here to convince you that the left side of this is just going to be t. It's the right side that we're going to do a little work on, right? I can bring the RC out front. I'll still have an integral from 0 to q of 1 over EC minus q dq. So I'm thinking u sub, probably the best way to go here. So I'll make my u equal to EC minus q. So du is going to be negative 1 dq. I knew I had to wait just an extra second for Tyler to make his full body convulsion agreement.
I was wondering what happened. I was thinking,
Whatever, hey, it's all in the video.
no.
You can replay it later. You can probably hear your agreement. It was very, very clear. So I'm gonna do a little substitution then in there, and we will get from. I know that you've learned now that I shouldn't leave my limits this way when I do U sub. I'm old school and don't care enough to change it. That okay so far? So I'm out of room. So here we go. I think that all of you know that the integral here is going to be the natural log. So the natural log. And I can go ahead and I have a negative sign that I'll just bring out front. I probably should have brought that out front already here. That would have made this a little easier. So let's put negative RC, natural log. I'll put my function back for u, which was EC minus q, evaluated from 0 to q. Am I good with that? To save some time, I'm going to do a couple of things all at once. I'm going to divide both sides by negative RC. And I'm going to put my limits into my logarithm. And I mean, this process we're doing right now is somewhat autonomous in that eventually they're all going to look like this whenever you have a natural log as your integral. We're always going to have our function buried inside here somewhere. So we're always going to be doing this process of combining the logarithm and then raising both to a base e. Remember, we want our function as a function of t. So to do that, we are always looking to find a way to raise both sides to the same base. This seems like the right way to do it. Now we want to solve for q. So I'm thinking multiply both sides by EC. Told you this is going to be really mathy, but understand that this is mostly just algebra. That doesn't make it easy, I know. And you guys get, frustrated when I say that, but it's still just algebra. Needing more space here. But we will finish on this final column. I'm going to solve for Q. So Q is going to be EC minus EC e to the minus t over RC. I'm going to factor out the potential difference and the capacitance. This is the charging equation. This is Q as a function of t. And if you'll look here closely, you're going to see a lot of the things we talked about at the beginning. First, at time 0. If you'll notice at time 0, that's going to be e to the 0 power. E to the 0 power is 1. So at t equals 0, Q equals 0. Now, this Q does represent the amount of charge on the capacitor. What is this product? We could write this as Q equals Q max 1 minus e to the t over RC. Indicate that's negative t over RC. Indicating that we know that we'll eventually reach a fully charged capacitor at some time in the future. Now, that time is when this term goes to 0. So the limit as e to the minus t goes to 0. When is that going to go to 0? Yeah, as t goes to infinity. So we know that you have to wait a long time for your capacitor to fully charge. Long time is kind of a relative term here, because it is technically true that we can never be at infinite time. Our time scales are based on this term here, RC. I want you to think to solve for it every time. Is it going to cut this for just a moment? I'm going to write it again. RC is often called the time constant, and it's given the Greek letter tau, because it controls how long it takes for our circuit to charge up. Generally, we don't measure when it's fully charged because, well, for obvious reasons, we can't. So we tend to talk about looking at what the time constant means for like a halfway charged capacitor. So to get an idea for tuning a capacitor, what it really means to tune the system, consider the halfway point. The halfway point will be whenever Q over EC equals 1/2. Do you understand why that's a halfway point? That's when Q over Q max is a half. This would be 1 minus e to the minus t over RC. So the 1/2 point kind of gives us a place to look, to get an idea of what it would take to make our capacitor charge faster or charge slower. So I'm going to solve this for t so we can see what the controlling factors are. And you're going to get not an unlikely response. You're going to get e to the minus t over RC equals 1/2. So minus t over RC equals the logarithm of 1/2. So t equals minus RC logarithm of 1/2. Now, I did this not because it has a lot of value for our circuit. It's to give us an idea of what it takes to charge our circuit, what will make it take longer and what will make it take shorter. The negative sign here is because the logarithm of any decimal is negative, right? So to ensure that our time is a positive number, the mathematics has to work out to provide that for us. And I hope all of you realize that this is just some number. What makes t longer is any times the resistance is longer, Or what makes T longer is any times the capacitance is longer. Or bigger. I guess we'll say that, bigger. So if you have a bigger capacitor, it holds more charge, it'll take more time to charge it. Does that make sense? If you have a RC circuit and you put a resistor in there, resistor restricts current. It'll take more time to charge your capacitor. Does that make sense? That's exactly what this says. If you increase the resistance, the time value gets longer. Increase the capacitance, time value gets longer. Now, this is a timing circuit. I want you to imagine something right now. Your calculator takes 5 volts to operate. You put 6 volts across it with the batteries that you put inside it. If you put an RC circuit in line with it, when you would hit the power button, the calculator won't turn on until the capacitor is charged, if your calculator drew its power from the capacitor. And what I mean by that is, going through all of this up, like, consider drawing my circuit a little different. If I put the switch here, and I put the calculator, say, in line with the capacitor, the voltage across the capacitor will be whatever the voltage across the calculator is. So if the circuit of the calculator was in line with the capacitor, they would see the same voltage. At time 0, the voltage here would be 0. Over time, the voltage across the capacitor would increase, so the voltage across the calculator would increase. I could choose when the calculator turns on by tuning the resistor and the capacitor. Now, I know you're wondering, well, why would I want to do this for your calculator? I want you to think of how many things in your life, when you turn them on, don't turn on right away. They take a few minutes before they actually switch on. You might want a delay in the system. Have you ever used your windshield wipers before? Ever have them on delay? That's all this is. It's an RC circuit with the windshield wiper here. The windshield wiper operates the moment the capacitor reaches the right level, discharges the capacitor, and then doesn't go again until the capacitor recharges. It has a dial on your usually on your turnstile thing, right? On your that dial is an adjustable resistor. Make the resistance smaller, it takes less time to charge the capacitor, the windshield wiper goes more frequently. Increase the resistance, takes longer to charge the capacitor, the windshield wiper goes less frequently. It's a timing circuit. The basis for anything that requires timing sits right here. Now be careful, it's a little more complicated than how I described, because when I put the calculator there, it does change the system a bit, right? The calculator is not like it has 0 resistance or something like that. It's a part of the circuit. But I wanted to give you an idea of what the functionality is here and the importance of the time constant. RC is considered the time constant. Now, a couple of points of order. Q as a function of T equals Q max times 1 minus e to the minus T over RC. This is the charging equation. It's not on your equation sheet. It's not necessarily worth committing to memory as long as you don't mind. You have to calculate for it. That's not really what happens on the exam. So I wouldn't say you have to worry too much about, getting this memorized. But you should notice we've seen this before. Right? You drop a coffee filter in the air, it reaches terminal velocity under the same curve. It's exactly the same. What do you think the result of dq dt is going to produce for us? Nobody? Oh, that makes me sad. Because by definition, this would have to be the current in this circuit. Right? dq dt is current. This should be the current through the resistor. Take a minute, take the derivative of this function. Moving on, Q is a constant, so I'll just pull it out, and I'll get Q max, and then I'll have d dt of e to the minus t over RC. Well, 1 over RC is just a constant. I'm going to have to use the chain rule on this, right? Which means I'll get Q max e to the minus t over RC, and then I have to multiply by the derivative of minus t over RC, which last time I checked is just minus 1 over RC. So this is not that hard. You're not being able to do it makes me crazy. Yes, ma'am.
Wouldn't there be a negative in front of Q max?
Well, it would cancel out.
Oh, you're right, there would be. That negative sign would be right here. Thank you. It is going to cancel out, but I need it to cancel out. So now, if I was to bring it all together, I'll get I equals Q max divided by RC times e to the minus t over RC. However, if you're really paying attention, and some of you are, which is why I like you guys, you'll look over here and you'll realize I wrote this wrong. No, I didn't. It's right. And Q max is EC. So the C's cancel, by the way. So E over R. Who can tell me what that is?
Oh,
Yes.
it's current.
It sure is. E over R is Ohm's law. It would be I max.
It's crazy.
It is. It is crazy. It is crazy. That's exactly what I was hoping you'd say.
Wait, IMAX? Like at the movies, right?
Hold on. Remember, V equals IR. Correct? So, if there was no capacitor in the circuit at all, this would be the current in the circuit if there's no capacitor. So, if I go back to the way this looked a moment ago, what this tells me is that at time 0, I get a maximum current that is equivalent to as if there was no capacitor at all, which means the current is fully regulated by the resistor. But that an instant later, I get exponential decay, and eventually the current will drop to 0 at infinity, governed by the same time constant that controls the rate that the capacitor charges. So in closing, RC circuits are timing circuits. They are very sensitive timing circuits. Their charge has what's called a rise time, the time it takes for the capacitor to become charged. The reason is simple. If you look at the graph for charge over time, you get the asymptotic function of the exponential, with this being Q max. At the same time, current is a function of time, we're going to get an exponential decay. We know that the current will immediately begin to degrade the moment the switch is closed. With I max being given by the voltage over the resistance, and Q max being the voltage times the capacitance. All right.